Welcome everybody to our video on polynomial addition and subtraction. So really to begin with, we can ask the question, what exactly is a polynomial? And for that, a polynomial really consists of terms. Now, a term for a polynomial has two parts to it. It's got a number part called the coefficient, and it's got a variable part, which is just variables maybe raised to some powers. Now, those two parts, the coefficient and the variable, are put together with the operation of multiplication. So maybe when you see things like a negative 3x to the second power, 4/7 x to the fifth power, 3x squared y to the fourth, you're seeing the number parts, so those are the coefficients. You're seeing the variable parts, and they're raised to powers. And the operation that you're seeing putting those numbers and those letters together is the operation of multiplication. Now, the important thing that actually makes a term for a polynomial a real term for a polynomial is that the powers on the variables have to be nice. Now, what we mean by nice is that you either don't have a variable, so it is just a number, or that the variables are going to be positive integer powers. Now, what are those? Are just 1, 2, 3, 4, 5, 6. So when you hear somebody talk about those nice numbers, they're just the positive integers, the ones that are counting numbers, basically. And so kind of what we've got as a review for the anatomy of these polynomials, that you've got coefficients and variables, and those things are going to be put together with the operation of multiplication. And then you've got the terms, which if you've got a bunch of polynomial terms, you put those together with the operation of addition, and that's how you get polynomials. And so when you see things like x to the negative 3 power or y to the 1/2 power, those are not going to be terms of polynomials because the powers are not nice. And so we're just going to take these polynomial terms, so coefficients and variables that have nice powers to them, and we're going to put them together with the operation of addition. Probably a reasonable question to ask at that point is, well, why exactly are we only working with multiplication and addition? And so the reason for that is that multiplication and addition have some really nice properties, and in particular they've got the properties of associative property and they've got the commutative properties. Now, just to kind of refresh your memory a little bit, what was the associative property? That just says if we're adding three things together, it really doesn't matter how we group them to add them together. We can either add the first two terms together, and then add the third, or we can add the last two together and then add the first. Same thing with multiplication. If we're multiplying three numbers together, it really doesn't matter whether we multiply the first two numbers, then multiply the third, or whether we multiply the second and the third and then multiply the first. The associative property says that we're going to get the same answer either way. So that's a nice property to have. So it really just means that when we're writing things like 2 times 3 times 4, it's going to be 24, and we don't have to have these parentheses to tell us what order that we're doing things. Same thing for the commutative property. Is really just, it doesn't matter whether we do a plus b or b plus a, whether we multiply a times b or b times a. 2 times 3 is going to give us 3 times 2. That's a wonderful property to have. It makes things a lot easier. We're kind of used to that. We use it without really thinking, but those properties are not always true for things like subtraction and division. So when we try to do stuff like subtraction with the commutative property, we would do something like 2 minus 3 is going to give me -1, but 3 minus 2 is going to give me 1. Different answers. I can't just switch the order and get the same answer. Same thing with division. 6 divided by 2 is going to give me 3, but if I try to do 2 divided by 6, now I get 1/3. Not the same answer. So I don't have that ability to just switch the order for subtraction and division. That causes things to get messed up. Same thing for the associative property, that if I would try to do 2 minus 3 minus 4, well, if I do 2 minus 3, that's going to give me negative 1. Then subtract the 4 is going to give me a negative 5. If I just regroup those, 2 minus the 3 minus the 4, so 3 minus 4 first is going to give me a negative 1. 2 minus the negative 1 is 2 plus 1, which gives me 3. I get a different answer. And so I don't have this really nice property of just being able to put things together however I want to with subtraction and division. It doesn't work that way. So subtraction and division don't have those nice properties that makes things easier to work with. So we don't put things together with division and subtraction. We lose those kind of nice properties like that. Kind of another thing with our polynomials that they are kind of generalizing ideas, and it's really a generalizing idea of our placeholder. Now, when you were learning the places for numbers, if we had something like 5,000, 54,321, well, we had place value for each one of those digits. We had the ones place, the tens place, the hundreds place, the thousands place, the 10,000s place, and so on and so on. Now, each one of those places was really going to be a power of 10. So the tens place was just 10. The hundreds place was 10 times 10, which was give me 100, so it's 10 squared. The thousands place is going to be 10 times 10 times 10, so 10 to the third power. The 10,000s place, 10 times 10 times 10 times 10, so 10 to the fourth power. And so if I were really writing something like 54,321, if I kind of write this out using all of those placeholders, it's going to be 5 times 10,000 plus 4 times 1,000 plus 3 times 100 plus 2 times 10 plus the 1. And if I kind of replace those numbers with the powers of 10, I'm going to have 5 times 10 to the fourth power plus 4 times 10 to the third power plus 3 times 10 to the second power, plus 2 times 10 plus the 1. Well, there's really not that much of a difference between writing it that way and writing 5 times x to the fourth power, plus 4 times x to the third power, plus 3 times x squared, plus 2 times x plus 1. So polynomials are really just kind of this generalization of the placeholder that we use when you were learning about your numbers way back at the beginning. So we're just kind of extending that a little bit. So adding polynomials is really just essentially combining like terms. And so now we've got this, what is this like term? Well, what makes things like? We have the variable parts, they match exactly. And so if we got something like 2x to the fourth power, 7x to the fourth power, if we look at the variable parts of that, they're both x to the fourth power, they both match, so they're both like terms. If we had something like 2x to the fourth and 7x to the third, well, now the variable parts don't match. One of them has a fourth power, one of them has a third power. That's not the same, so they don't match. They're not like terms. And the important thing about them being like terms is that we're able to use our distributive property to put those things together. Now remember what the distributive property said, that if we had A times the quantity B plus C, that was just going to be A times B plus A times C. So we had the A multiplying both of those terms. Well, we're kind of going to use that distributive property in reverse when we're combining them, that if we had 2x to the fourth power plus 7x to the fourth power, that's really just the x to the fourth is multiplying both the 2 and the 7, and so the distributive property says that's the exact same thing as if we had 2 plus 7 times our x to the fourth. And so the 2 plus 7, we know how to add those together. 2 plus 7 is going to give us 9, and so we combine those like terms, 2x to the fourth plus 7x to the fourth as 9x to the fourth. And so The distributive property kind of lets us put those things together, maybe not necessarily even really thinking about this middle step, but we're just seeing that both I've got 2x to the fourths and 7x to the fourths, so how many total do I have? I've got 9 of those things. And so because the placeholders match, I can put things together. So some examples of those, if I had 3x squared plus 4x squared, well, the x squared, the powers match, so they're multiplying the same thing. I can just really factor out that x squared, so that's going to be the same thing by the distributive property as 3 plus 4 times x squared. The 3 plus 4 gives me 7x squared. If I had 5y to the 5th power plus 6y to the 5th power plus 7y to the 5th power, well, I've got y to the 5th multiplying each one of those, and so the distributive property says that's the same thing as 5 plus 6 plus 7 times y to the 5th. Well, 5 plus 6 plus 7 gives me 18, so I have 18y to the 5th. And really, I'm getting that by kind of this shortcut of just adding 5 plus 6 plus 7 because the variable parts match exactly. So that's kind of the key thing. I'm looking for the variable parts to match, and then I can just do the operation with whatever the numbers are. So if I, third example, if I had this 2w to the 4th plus 6w to the 4th plus 3w squared, well, now I have some like terms. I've got a w to the 4th and a w to the 4th. I can put those together, but the w squared is different. That's not a w to the 4th. I can't combine it. I have to just leave it separate. Okay? And so I can put the 2 and the 6 together to give me 8w to the 4th plus the 3w squared. And so the 3w squared is out there. I can't combine it. It's not a like term with the w to the 4th. And so that's my final answer. I can't put them together because the powers on the w's are different. So when we're doing the polynomial addition, kind of the idea is that we are just combining the like terms. We're grouping the variable parts that match together. And so if I had something like 2x to the 3rd power plus 4x squared plus 3, and I was adding on 5x to the 3rd power plus 7x squared plus 6, I'm going to see which ones end up being like terms. Well, my powers of 3, my 2x to the 3rd power, and my 5x to the 3rd power. I've got like terms in the 4x to the 2nd power and the 7x to the 2nd power. And I've got like terms in just the numbers themselves, the 3 plus the 6. They're just numbers, they don't have variables on them. And so kind of I rearrange things, put those like terms together, 2x to the 3rd plus 5x to the 3rd. I'm putting together the 4x squared and the 7x squared, and then I'm putting together the 3 and the 6. Well, the distributive property says that that's going to be the same thing as 2 plus 5 times the x to the 3rd power. Now notice these are only the powers that match are going together. 4x squared and 7x squared, well, the 4 plus 7 times the x squared, and the 3 plus 6, I can put that together to give me 9. And so the 5 plus 2 gives me a 7x to the 3rd power. So 4 plus 7 is going to give me an 11x squared, and then plus the 9 as the final answer. Now, to kind of, again, hammer home this idea that I'm really just treating the powers like placeholders, I could really group these things into columns as well, so it looks more like I'm just doing my usual arithmetic. So if I've got my 2x cubed plus 4x squared plus 3 plus my 5x cubed plus 7x squared plus 6, well, I can line the powers up into columns. So I can write out my 2x cubed plus 4x squared plus 3, and then I'm writing the terms from the second polynomial directly under the terms that match the powers. So What's going to go under the x cubed column? Well, I've got a 5x cubed. Plus, which term is going to go under the squared column? The 7x squared. And what's going to go under the 3? Well, the term that doesn't have a variable on it, the one that matches. It's just a number. It's just the 6. And so now I can add them into columns, kind of like my usual arithmetic. 2 plus 5 gives me 7x cubed, plus 4 plus 7 gives me 11x squared, and then 3 plus 6 gives me 9 on the end. And so my final answer is just going to be the 7x cubed plus 11x squared plus 9. And so if we want to put them in columns, then it's probably best for all the powers to be there, even if they're not necessarily written there in the original problem. And that's kind of what we see in this example. So suppose we've got our 7x cubed plus 4x squared plus 2 plus 6x squared plus 4x plus 1. Okay. If we look at that first polynomial, the 7x cubed plus 4x squared plus 2, that thing is actually missing a power of x. Okay, so it doesn't have just a single x in it. It's got a third power, a second power, and no variable, but it doesn't have just a plain old x, an x to the first power in there. And so if we want to put them in columns, we may have to add in kind of like the 0 placeholder that we put in for our numbers. And so if we're adding our 7x cubed plus 4x squared plus 2 plus our 6x squared plus 4x plus 1, then if we're listing those out in columns, then we might want to put a column in there for the x power. So we'd have 7x cubed plus 4x squared plus a 0 times x plus 2. The 0 again is kind of acting like a placeholder for our usual numbers. Now when we're putting all of the other powers that are in there, we've got a column for the x from the second one, from the second polynomial. So underneath the x squared column, we're going to put our 6x squared. Underneath the x column, we've got our plus 4x. And underneath the number column, we just have our 2 plus 1, our plus 1 from the second polynomial. And so what we have then, we can just add our columns together now. Well, 7x cubed plus 4 plus 6 gives us 10x squared plus 0 plus 4 gives us 4x plus 2 plus 1 gives us 3. And so for our final answer, we would have 7x cubed plus 10x squared plus 4x plus 3. So kind of another example of that. Suppose we want to add together 5x to the fourth plus 3x squared plus 2x plus 7. And to that we're adding on 4x to the fourth power plus 6x cubed plus 8. Well, if we want to put them in columns, then we're writing all of the decreasing powers from the largest all the way down to just the number. So we've got our 5x to the fourth. We don't have an x cubed, so we have a 0x cubed plus our 3x squared plus our 2x plus our 7. And now we put the terms from the second polynomial under the correct columns. So we've got our 4x to the fourth column plus our 6x cubed column going under. Then we don't have an x squared, so we can have a plus 0x squared plus, we don't have an x, so we have a 0 times x plus the 8. And so if we add those together, 5x to the fourth plus 4x to the fourth gives us 9x to the fourth. 0 plus 6 gives us a plus 6x to the third power. 3 plus 0 gives us a plus 3x squared. Plus 2 plus 0 gives us 2x. Plus 7 plus 5 gives us 15. And so for our final answer, we've got 9x to the fourth plus 6x cubed plus 3x squared plus 2x plus 15. So how might it look if we wanted to put everything on one line? Well, if we had our 5x to the fourth plus 3x squared plus 2x plus 7 plus our 4x to the fourth plus 6x cubed plus 8, if we want to put them all on the same line, then we're really just, again, kind of starting with the highest powers and going down, decreasing all of the powers. The only difference here is that we don't necessarily need the placeholders because everything is on one line for the 0 placeholders. And so we're putting our highest powers, our x to the fourth powers, so 5x to the fourth plus 4x to the fourth. Then we don't have any other x to the fourths. So then we look at third powers. Well, we've got 1x to the sixth, or 6x to the third power. So we've got 1/3 power. So we have our plus x to the third. Our x squared powers, we've got only 1x squared, and that's our 3x squared. Then for our x powers, we've only got 2x. So we've got 1x power, and then we've got our two numbers, our 7 and our 8. And so we just kind of write those in decreasing power order, putting all of the like powers together. So that 5 plus 4 gives us 9x to the fourth. 6x cubed plus 3x squared plus 2x plus 7 plus 8 gives us 15. And so we can, with a little bit of practice, we can put everything together on one line, group the powers together, then it's easier to kind of look at them and combine them. And so kind of the bottom line is either method is going to work, and so you really look at them, see which method you like better, and use that one. So in this case, there's not really one right answer, one best way of doing it. It's what way actually works for you and how you think. Okay. So kind of moving on now, what about subtraction? I mean, all of our terms have been positive. We've just been dealing with positive numbers. So how do we deal with subtraction? And the honest answer with that is that we really look at subtraction as being an abbreviation for negative numbers. And so kind of reminding a little bit, with words, when you see the word can't, you know that that is really just going to be an abbreviation for the two words cannot. If I see the word shouldn't, I know that that's just going to be the abbreviation for should not. And so when I see something like 7x squared minus 4x, I know I'm putting everything together with addition, and so that's really just an abbreviation for 7x squared plus a negative 4x. And kind of likewise, if I've got 6x cubed minus 3x squared, it's not really the operation of subtraction. I'm using that as an abbreviation for 6x cubed plus a negative 3x squared. And so by keeping the negatives on the numbers, now we can move things around, still using our operation of addition, but keeping everything still mathematically correct, and so that however we move things around, we will be able to have the same answer. And so let's see how that would work with an example like 7x squared minus 3x minus 4 plus our 3x squared plus 4x plus 9. Well, in this first polynomial, we see things put together with the operation of addition, so we write it out with our without using the subtraction abbreviation. So we have our 7x squared plus now a minus 3x plus a negative 4, and so that we're making sure that we're seeing those terms together, seeing those as one term, we put parentheses around those negative numbers so that that's our signal in our mind that we are grouping those together and that it's a negative 3 inside there. And so for our other terms, we've just got our 3x squared plus 4x plus 9. And so the 7x squared, so now we are able to write our powers. We can regroup them together so that we would have the 7x squared plus our 3x squared, so those are our x squareds. Then for our x power, or just our plain old x's, we've got a plus the negative 3x plus the 4x, so we've got those two together, and then we've got plus the negative 4 plus the 9. Okay. Now we've kind of rearranged those, grouped them together, so the 7 and the 3 gives us 10x squared plus negative 3 plus 4 gives us a plus 1x, and the negative 4 plus 9 gives us a plus 5. And so when we write our final answer, we don't really have to multiply, we don't really have to write the 1 in there. We can just write our final answer as 10x squared plus x plus 5. And so when we are subtracting polynomials, what subtracting polynomials really is nothing more than distributing a negative 1. And so remember, when we're distributing something, if we had something like 2 times the quantity 3x plus 4, the distributive property says that that's going to be 2 times the 3x, and the 2 is going to get distributed to the 4, so that we've got 2 times our 3x plus our 2 times the 4. Now the 2 times the 3x just gives us 6x. 2 times 4 gives us 8, so our final answer is just 6x plus 8. So when we subtract polynomials, we actually write it with the subtraction abbreviation. So if we start off with something like 5x plus 3 minus the quantity 2x plus 1, what we're really saying there is that this is 5x plus 3 plus a negative 1 times the quantity 2x plus 1. So we kind of rewrite and get rid of that subtraction abbreviation so we can see what's going on. And so what does the distributive property say? It's going to be the negative 1 times the 2x and the negative 1 times the 1. So we have 5x plus 3 plus our negative 1 times our 2x plus our negative 1 times the 1. Well, the negative 1 times 2x just gives us a negative 2x. The negative 1 times 1 just gives us a negative 1. So we have our 5x plus 3 plus a negative 2x plus a negative 1. Still, everything is put together with the operation of addition. We just have the negatives there so that we can move the signs around and not change our answers. So we're getting 5x plus the negative 2x. Well, 5 plus a negative 2 just gives us 3x. Then we've got a 3 plus a negative 1, which is going to give us a positive 2. So our final answer is just 3x plus 2. So working another problem, suppose we have our polynomial negative 7x minus 9 minus the quantity negative 2x plus 9. Well, again, we rewrite this, removing the subtraction abbreviation. So we've got our negative 7x minus 9 plus a negative 1 times the quantity negative 2x plus 9. So the distributive property then says that's going to be a negative 1 times a negative 2x, and it's going to be a negative 1 times the 9. So we have our negative 7x minus 9 plus the negative 1 times negative 2x plus the negative 1 times the 9. Well, negative 1 times a negative 2x gives us a positive 2x, and the negative 1 times 9 gives us a negative 9. Okay. So then kind of getting rid of the subtraction abbreviation from the first polynomial, we've got a negative 7x plus a negative 9 plus a 2x plus our negative 9. Well, we rearrange things and put all of the like terms together. So we've got a negative 7x plus a 2x. Then we've got our negative 9 plus our negative 9. Well, negative 7 plus 2 gives us a negative 5x, plus negative 9 and negative 9 gives us a negative 18. And so for our final answer, we write our final answer with the subtraction abbreviation so that we don't have these extra parentheses, and we've got negative 5x minus 18. And so kind of looking at one more final example, if we've got something like x squared minus 6x plus 7 minus the quantity negative x squared minus 3x plus 5, Then again, our first step so that we're seeing things correctly is to get rid of that subtraction abbreviation. So we've got our x squared minus 6x plus 7 plus a negative 1 times our quantity, negative x squared, plus a negative 3x plus a 5. Okay, so our negative 1 gets distributed to all three terms. That's distributive property. So we have x squared minus 6x plus 7 plus a negative 1 times a negative x squared plus a negative 1 times a negative 3x plus a negative 1 times the 5. And so the negative 1 times negative x squared gives us a positive x squared. Negative 1 times negative 3 gives us a positive, so a plus 3x, plus a negative 1 times 5 gives us a negative 5. And so if we get rid of the subtraction abbreviation in the first polynomial, now we've got our x squared plus a negative 6x plus 7, plus our x squared plus 3x plus our negative 5. Putting the like powers together, we've got our x squared plus our x squared. We've got plus our negative 6x and our 3x, because those are like powers. And 7 and the negative 5, because those are just numbers. And so x squared plus x squared gives us 2x squared. Negative 6 plus 3 gives us a negative 3x. 7 plus the negative 5 gives us a positive 2. And so for a final answer for our 2x squared plus a negative 3x plus 2, we can rewrite it with the subtraction abbreviation again for our final answer to give us 2x squared minus 3x plus 2. And so when we're doing this for making our manipulations, we are getting rid of the subtraction abbreviation, writing out everything with addition. We're combining our like terms, and then when we write our final answer, then we go back to using the subtraction abbreviation so that we're writing fewer fewer parentheses in our final answers. And so this has kind of been a little bit of how you go about adding and subtracting polynomials. I will see you guys next time.